let me see here. I'm going to start recording. I'm going to admit a few more folks, and then as they start popping in, I'll record. Yeah. As they start popping in, we'll go from there. So, well, you guys probably don't need to see that. That's a little bit later on. All righty, here we go. So welcome back. Tonight is going to be another interesting one, I think, I hope. We didn't get a chance to do this in some of my other classes the last few times we run this, just because some of the things didn't exist yet. But now they do. And so you guys get to help me out and try playing around with some new equipment and tools. And we'll kind of get to that right at the beginning of tonight's class. But tonight's class is all about groundwater in the context of Central California, and maybe a few little, just some background information on all the water players in California. It's going to be an interesting year, right? We're heading into another drought. There's already, like, the snow is pretty much gone at about 6,000 feet in the Sierras. There should still be a lot. Our snowpack is 40% of normal or something like that for this time of year. So we're going to be relying heavily on pumping groundwater because there's not as much water coming into the rivers. So it's something to think about. I think it's very useful, especially as just a member of our society here in the Central Valley, right? So maybe we can keep everybody accountable, learn some different ideas from different sectors, or agricultural, city users, urban users that use the city water, things like that, environmental uses, all those different things. All right. So I'm trying to multitask and let people join at the same time. So I apologize. Okay. So some things to accomplish today then is just some of that geo news for you to geo knows, maybe a quick little vacation share here. Some groundwater modeling investigations, historical water context, all that good stuff. Oh, and tonight, so don't have a panic attack, but I'm going to kind of just give you a brief introduction to kind of this final project that we're doing. It's not hard. It's not bad. Next week, we'll go into it in more depth and detail, but tonight is just kind of throwing it out there, letting you mentally get like, oh, what do I need to do? It's basically, you're going to be making a Google Earth project with 5 separate stops. All right. It's pretty basic. It's pretty easy, but I want you guys to have that practice because it's a useful tool if you ever become a teacher, to be able to use this and, share ideas and things, just like you guys have been using Google Earth in this class quite frequently. It's going to be a way for you to make stuff like that. So don't stress out. Don't panic. It's not something I'm trying to add on to your plate to make it like the end of the world or anything like that. I'll hopefully, as I try to do the rest of the class, I'll make it easy enough to understand so that it's not stressful. It should be kind of interesting. All right. So maybe even fun. That's the idea. And so for our, what do you call it? The sketch notes for tonight, this is kind of the idea. We're going to start out looking at porosity and permeability, these concepts that we've talked about a little bit in soil. We'll have you guys do some modeling of infiltration and runoffs in a breakout room. Then you guys are going to get in and use some other models looking at wells and how water actually gets into the ground. It's pretty cool, fun. It's not a game, but it's a model that kind of resembles a game. Talk about aquifers and water tables, the problem with clay in the Central Valley with our aquifers. And then kind of, once you know everything, what are some things that you think we could do? What are some strategies that might help us maintain sustainable levels of groundwater in California? And I'll just tell you right now, we've already enacted the State Groundwater Management Act, which goes into effect in, I think, 2044. So it gives people a lot of time. The agencies that manage our groundwater, gives them a lot of time to basically plan and make sure that we can be sustainable for the future. I don't know if you've read in the news, but Las Vegas just last week, banned grass that only gets walked on when it's mowed. So this decorative ornamental grass. And I think that's probably going to be something that happens in California very soon, is that lawns will go the way of the dodo, and we'll find some other water management stuff. So holy cow, it's been 2 weeks. There's a lot of things that have happened between since we left and when we came back. And I came back from my vacation a week ago and it's like, man, it's been a week already. It didn't even seem like that. But one of the first things that happened on our vacation was down on the island of St. Vincent, which is, well, let me show you. Down, that's Iceland. We're not going to see Iceland yet. Not trying to make everybody sick here. Oops, let me see. Somebody said chat. Oh, yeah. So somebody asked also about receiving updates on the grades. So remember, your grades are pretty much so far the sketch notes, right? So if you've gotten all those done, I'm totally caught up with all the grading on the sketch notes. So in those comments, you should see the scores. If you go into the slides on your sketch notes, you can see those scores. If you don't find them or don't see them, you can just like hang out after class really quick and I can bring up the spreadsheet and kind of show you all that stuff. But that's how that's going. And then the final project's going to be like 10% or something like that, 10 or 15%. And it's pretty easy to do. And we'll have a presentation and all sorts of fun stuff that go around with that. So that's where your grades are doing. Everybody's doing fine. I mean, for everybody that's turned the stuff in, I would say like 95% of everything is turned in. There's a few missing weeks here and there from some folks, but I know we're all just working to get it done. So get it done when you can and we'll be okay. And you can always turn it in without like penalty, right? Just let me know so that it doesn't go. I always try to go back and check, but just send me a note if you fix anything to get those points back. So sorry, that was came up in the chat. So right here, St. Vincent is this island out in the Caribbean here. And this is La Soufrière, which is, well, you guys tell me, what kind of volcano is La Soufrière based on the shape that you guys are seeing here? Let's apply some of the things we've learned in this class. What kind of volcano is that? Like, oh man, I gotta thumb through all those sketch notes. I know you know it because you put it in sketch notes and things. So it looks like it's pretty steep, like that. Somebody can write up, let me see here. You can chat it, you can say it directly and unmute. It's up to you guys. Cinder cone would be a good guess, except cinder cones. Let me, oh, I don't have a measuring tool on this one. Oh wait, yeah, I do. Here's a measuring tool to give you an idea. That's meters.
Is it a stratovolcano?
Yeah, all right, you got it. So this is stratovolcano. So it does look much like a cinder cone, except the thing that gives it away here, not nautical miles. I just want miles. There we go. There we go. It's about 5 miles across and several thousands of feet tall. So it's a little bit bigger than cinder cone. And then somebody else said a plug dome too. And if you look at the inside, you're totally right. All this little forest stuff right here was growing on top of the cinder or the plug dome that was inside of this stratovolcano. And you can tell in the past it's had some explosive eruptions. I mean, here's one crater, and then you can kind of look over here where it looks like there was also another crater, like it made a caldera at one point and it collapsed and then has built up again over time. Well, it had an eruption. Its last eruption was like 1912. And then this weekend it did, did that. But I put the link on here too for, it's a Science Friday link. But this is what it looked like last week, April 9th or so, so almost a week ago. Just this, they had a massive, just a massive ash column go up. And some of this went over 25,000 feet up into the atmosphere, into the stratosphere, basically. And when you get particles of ash and sulfur dioxide that get that high, as it starts spreading out around the globe, if it's a big enough eruption, it can actually act like a sunscreen and prevent some of solar radiation getting into the Earth's surface, and it can cause temporary cooling. So I think this is a VEI, a volcanic explosive index. I think it got up to a 5 or maybe a 6, or I think maybe a 5 is, if I remember right. So it's a pretty decent sized volcanic eruption, one of the bigger ones we've had in the last couple decades, I think, somewhere in that neighborhood. But one of the fallouts, there's lots of ash falling on the streets of St. Vincent. They've had pyroclastic flows. Now, Dr. Scarlett, Jasmine Scarlett here, she's the one that's featured in this radio interview on Science Friday this afternoon. Her PhD dissertation, because she's from St. Vincent, was on volcanic warnings using those tremors and everything that we learned about in class. Guess how many people this volcanic eruption, this huge volcanic eruption, guess how many people it killed? There's 30,000 people that lived around this volcano, or that live around this volcano. What do you think the casualty rate has been? So, any guesses? You can just unmute or type it in. You can see there's villages everywhere. There's their airport. Let's see, who wants to take a guess? How many people were hurt or injured? Oh my gosh, where's my thing? There it is. Sorry, 1. Danielle says 1. And as far as I know, as of yesterday, I haven't checked today, but as far as I know, as of yesterday, there have been 0 people killed by this volcano. And it all has to do with, basically they had this volcanic warning system. The University of West Indies that's down there monitored this very heavily. They saw the change in the harmonic tremors and were able to evacuate everybody. So nobody has died from a very large volcano. And it's a really cool testament to the science and the folks listening to the experts to clear the area. They got out, they evacuated about 13 hours before the eruption happened. So all the stuff that we learned and that you learned, it's paying dividends for these folks. And if something like that ever happens in California, it's the same kind of thing that will happen. And then I just want to show you one, another, by the way, that's what I was going to ask. I almost forgot. Let me zoom out. Let me get our north pointing in the way that you're used to seeing it here. So the United States is over here. Here's Cuba and all that stuff. What is causing this stratovolcano to form? What process out in the ocean between these plates? What tectonic process is causing that stratovolcano to happen, to make those chain of islands that are volcanic? What's going on there? And that dark area right there should give you a clue that kind of stitches out over here into the ocean. Let's see, I know I'm taxing everybody's memories and brains. Think back to our tectonic simulators, smashing plates or pulling plates apart. You guys remember? It starts with an S. Convergent boundary. All right, so Danielle says convergent boundary. It is a convergent boundary, but it's a special type. So it's oceanic plate and well, actually, there's a small little oceanic plate in here too. So yeah, it's an oceanic plate to oceanic plate, but one is more dense. And so you guys remember what the S word is when the plate goes down? Yeah, there you go. You got it, subduction. So this is a subduction zone right here. And we're seeing the volcano. So every one of these islands has their volcanic in origin right here, which is pretty amazing and pretty interesting. So on the other side, not the other side of the earth, but in the middle of the Atlantic, just a few thousand miles away, I'm trying to make you sick, back to Iceland. I think right before we left, this was starting to go, but remember the mid-ocean ridge in the middle of the Atlantic Ocean where the spreading zone, where the plates were rifting apart and splitting apart? Well, Iceland, just so happens that mid-ocean ridge goes right through this part of Iceland right here. It's rifting apart. And here's what it looks like right now. This is live video as we speak or as I talk from Iceland, because Iceland is awesome and they put up all these live webcams. But I think there's 5 or 6 fissures. And notice it's basaltic lava. It's the very kind of runny, there's spattery a little bit here, but these are only a few 100 feet high spatter cones. The lava flows are running everywhere. It's not the big explosive thing that we just saw in La Soufrière. So it's kind of cool to see both types of volcanoes happening simultaneously. There's also volcanoes in the Canary Islands erupting right now, very similarly to this. And there's one up in Alaska as well that's erupting more like La Soufrière, which is a very explosive composite volcano. So the Earth is active. Oh yeah, go ahead.
I have a question about that. Is that the same one that like started erupting a few weeks ago?
Yep.
How long does it go for?
So that's a great question. You know, in Hawaii, in Mauna Loa, that one was over 30 years in a row, and now it started back up again. So it's been for another 1.5 years or so. they're doing geochemistry analysis of these lavas, and it's coming from very 14 or 15 miles down, which it's a pretty big conduit to be able to tap into. So some of the geologists, nobody really knows for certain, but it seems like it could go on for more than a year at this rate, the way things are going. So fingers crossed, because if that's the case and we're all vaccinated, I'm taking Iceland Air to Iceland in next Christmas break or something, and going to take pictures of the northern lights with the volcanoes going off in the front and poking some lava. I really want to poke some lava. But anyways, so that's kind of where we were, or not where we were, but that's Iceland. And then just to kind of share and brag one quick thing before we get super started. Over here in Northern California is where we started going this past vacation. We went into Lava Beds National Monument, into this place called Golden Dome right here. And this came out of the Medicine Lake Shield volcano. So you can see all the little or the cinder cones popping around everywhere else. But here's the big shield volcano. And it had these lava flows that made lava tubes that drained out that I talked about a little bit earlier. But, oh, there it is. I'm going to admit them. There we go. So this is kind of the experimental stuff I like to do. And I just want to show it with you guys. And there's a link. I'll put the link in there if you guys want to. But this is a super high resolution photosphere, kind of like Street View, except what's really cool about this is you can zoom in and give it a second to download a little bit. And it just keeps zooming. And this is called Golden Dome because it's not made of gold. The gold is not actually like the mineral gold. It's bacteria that is hydrophobic. And when the water gets on top of the bacteria, it kind of reflects this golden color underneath your headlamps and lights when it shines on it. But it's kind of all over the place in this dome. And so if you want an experience to go see it, you can totally go put this on yourself. Or if you have Google Cardboard or something, you put your phone in that viewer or an Oculus at home and see what's there. So pretty cool. I'll have more of these a little bit later on, but that's where I spent my time, was there. And then where you see the waterfalls, Bernie Falls, we had some good volcano time with my family this spring break. And it was so awesome to get away and not see very many other people and have fun. So highly recommend listening to this Jasmine Scarlett interview. She's a really cool PhD student, or just got her PhD, so she's no longer a student, but volcanologist who's awesome. All right. Whew. Okay, so thanks for listening. It's just kind of neat when things that we talk about happen in the real world. So I just wanted to share. And then so now I'm going to give you like 3 or 4 minutes worth of background, and then we're going to get you right into your breakout rooms and you're going to start playing around with some things. So if you were to take a cross section of the Central Valley, the San Joaquin Valley, and cut it in half, basically you have the granitic rocks of the Sierra over here on the eastern side. And then we have all those sediments that washed off of the Sierras, right? The granite-based ones, so your clays, feldspars and quartz and things like that, but the clays that decompose from those, and some of the silts. And this makes a lot of what we grow our agriculture on in Turlock and this part of the Central Valley. And then if you were to go across the San Joaquin River over here, you'll notice that these sediment colors look different. And that's because those are the sediments that have come off the Coast Range. And those were former ocean sediments that have been uplifted due to tectonic forces and have now eroded down and done that. Geez Louise, my wife is having allergy problems, it sounds like, so sorry. But if you take a cross section, you'll notice, hold on, I gotta ask if she's okay. You okay? Okay. She's okay. It's just allergies. She went running around outside, I think, with my son. So anyways, if you were to take a cross section of this, we have a lot of sandier soils over here and a lot of kind of smaller sediments, silt and clay and things like that over on the western side that have a lot more salts and things in them. So we're going to kind of give the basics of this tonight. And what's kind of cool and really kind of interesting is at the base of all these sediments, are the old kind of rocks of the old trench that used in the Four-Arc Basin that used to be out where California is now. So remember where we live 200 million years ago was kind of that ocean trench area, or just outside of a trench of what we call Four-Arc Basin, where it was very deep and things were settling up and piling up on top of it. And so what's kind of cool is we have this hard impermeable rock, but we have the other rock that has sand that lets water and things through it. And these gray layers that you see there, those represent areas of clay where there was maybe periodic lakes at one time. So usually you find clays at the bottom of lake beds. So at one point they were areas where clays were deposited, and that's going to play a role with how we get water out of the ground and into our faucets or into agricultural use or using it in the city or things like that. So we're going to take a look at all this. Basically, where this water is stored underground, or where the water is underground, it's what we call our aquifer. So it's totally connected. So all of this water is connected under the surface of the earth. I mean, if you were to pump a lot of water out over here on this side of the San Joaquin Valley, theoretically, eventually you'd start drawing on water that's on the other side of the valley, because that water is going to flow downhill or follow a gradient, just like it comes out of the mountains. So just as a quick refresher, all right, how fast water goes into the soils is what we call the infiltration rate. And this is what I showed you a few weeks ago when we talked about the soils, but it's just kind of a refresher to see how fast water goes through kind of areas that have a lot more pore space. So these areas have a lot of pore space. They have vacant areas where water can fill down into it. And they have a lot of pore space that's interconnected so that the water can get down there pretty freely. As opposed to this one, which is more like a clay simulant. So when you pour water in there, you notice the infiltration is much slower, even though there's actually quite a bit of space that's in there. It's not super well connected because you have a lot of the pieces of clay, if you're looking at my hands, they kind of lay on top of each other and they prevent the water from connecting from one empty space to the next empty space. So it really prevents the flow from going super duper fast. So this is what we call the infiltration rate, or the permeability. All right, permeability is how fast it goes through, and the porosity is how much of, if you take some dirt, how much of that dirt actually has spaces or holes in it. All right, so let's, oops, doggone it, sorry, there we go. So here's a good way to visualize that. I just spent time using my hands because I don't know why, but I guess that's just me. So here's another way of looking at it. This would be on the right-hand side, an area that has not very good porosity, because that empty space, the pore space, the space between the grains here are kind of filled in with either sediment or dirt, or cemented together in some other way. This way, this one down here would have a lot of porosity where water is free to move. So this would be porosity. And then another way of looking at that permeability is how well that water can go and how well that water is connected between different grains, or different voids between those grains, boom, 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 kind of like Plinko going down, if you've ever watched Price is Right, right? So Plinko would be like good permeability, where it can kind of go down like that. Poor permeability means it gets blocked from time to time. So that's what we're talking about with porosity and permeability. So this brings us to a breakout room number 1. All right. So there's not a whole heck of a lot of us tonight. So I think, probably do groups of 4, 3 and 4, something like that. But this is a fun little simulator that you guys are going to use. So I am going to copy the link. Let me see here. Here's the Jamboard. And then here's the runoff simulator. Oops. And you can open them up really quickly if you want, and then I'll give you a second, and then I'll show you how to use these things. All right. So exit, 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 exit. There we go. So here's what we have. So on your Jamboard, it's kind of, I cut and pasted in the background, basically what the simulator looks like. So this is the simulator. This is the actual real working simulator right here. There's a couple of things to notice, right? Over on the right-hand side, you have this precipitation slider, which means, how much rain do you get in a 24-hour storm event, from not very much to a lot. The actual precipitation is noted up here in the top left-hand corner. So that says like 5 centimeters. 2 inches, 2.9 inches of rain, I think, is a little over 6 centimeters or somewhere in that neighborhood. That is like the record for one day of rain in Turlock in 24 hours is just about 2.9 or 6 centimeters of rain. All right, just to give you some perspective. An average rainstorm in Turlock would be about a centimeter of rain when we're looking at metric ways. Okay, so as you slide this, you'll see different things move around and change. And so I'm going to have you look around, figure out, what do these things mean? What do they say? Kind of hover over all of these different little areas over here, maybe read and try to figure out what those mean. And then what do these soil groups mean down here? So if you'll notice back on your Jamboard, so this is the Jamboard and not the website. So to open the model, hover over all those different components. What do you notice and what do you wonder about those component descriptions? So that's what I was thinking could be like general notices and general wonders. Just what are some of the general things you notice? And then it says, what do you notice and wonder about? How are they similar or different? So especially down here for the soil groups, or for some of these, like how is the forest different than the barren land? Or how is developed high density compared to like grasslands? What's those differences? And then it says, just play around with that model by changing all sorts of different things. What are some of the data supported things that you notice and wonder as you change it? So you'll notice there's on your model, there's lots of different places to find data and information. There's precipitation. There's some of these other fancy words that you can read off there. There's a bar graph. So there's all sorts of things to take a look at. So I think for this first one, we'll give you about 15 minutes or so, 15 or 16 minutes to play around and start popping your answers on Jamboard. Maybe it might be best to have one person share a screen. I don't think this is a super intensive, like it's like Google Earth or something that's going to crash your system or anything. And then see what you notice and see what you wonder. All right. So, oops, somebody got here just in time. I'm going to put you off into breakout rooms now. Let me know if you have any questions, but the directions are over on the left-hand side there again. Doggone it. There we go. All right, so 5 breakout rooms. That's actually better. Yeah, create, and then I gotta change this. So we'll go for 15 minutes here and see how that goes. All right. So say hi.
Hi, Professor. I have a quick question.
Yeah, go ahead.
Sorry, so I have we're gonna go get our COVID vaccine right now.
Oh, congratulations.
It's okay if I could leave because I know it.
That's way more important. Yeah.
Thank you. I'm so
It's
sorry.
being recorded and stuff, but yeah, you got to jump on that when you can get it. So,
Okay, I just feel so bad. Thank you so much.
yep, no problem.
Bye. Thank you.
Welcome almost back, everybody. Nice, awesome, man. You all got on a good roll there. So before I go into some of the other questions that I kind of had prepared, I just kind of like to start with anybody. So how about from your group? And I forgot to tell you this beforehand, so my apologies. But if somebody would nominate themselves in their group to maybe come up or talk about one of like the most interesting observation you've made or the most pressing question you have based on what you saw there, and we can just go through the groups, and it won't take too long because there's not too many groups tonight, but just 30 seconds or so to come up with that. And we don't necessarily have to go in which order, just tell me which group you're at and I can flip you through to the right Jamboard. So would anybody like to?
I just realized, I don't know what group I was in, but I was doing everything on the first one.
Oh, okay. Yeah. So that's the group. I guess that was group one. So
I don't know if that was my group though.
or well, your name's on there. So
Oh, okay, good.
yeah. All right. So did you guys what were some cool things that you guys noticed or observed? I have questions about.
We wanted to know what does evaporation means?
All right. Yeah. So evapotranspiration. That it's a funky, funny word. So that's good. That's one of the things I hope folks would ask. But so evapo is short for evaporation, and transpiration is what plants do. It's why there's like dew on the grass in the morning when you walk out there. As part of the photosynthetic process is, they make sugars in the plant and then they give off oxygen, and they also give off some water byproduct, water vapor byproducts. And so evapotranspiration basically lumps together evaporation that would just happen, like if there's a puddle on the ground and it evaporates over time because of the sun, or transpiration, which means it's water being sucked through the roots of a plant, being used in photosynthesis, and then some of those byproducts of the photosynthesis is water vapor going out into the atmosphere. So that's what evapotranspiration is. It's basically putting water molecules back into the atmosphere, either through evaporation or transpiration. So, and we'll come, if nobody else mentions anything about that, we'll come back in just a minute and I'll show you some other cool things to think about because it's important in our area. Good question. Another group.
We were wondering why when you had you changed the amount of precipitation, why it randomly, like if your runoff was really high, there was like an exclamation mark above your little meter. But it didn't say why.
That's a good question. You know what I think that means? I think that exclamation mark means this is like flood potential category. So it's where there's so much runoff that this is the type of stuff that can produce floods and damage like that. So that's a good question too.
We also wondered how does the water infiltrate into the ground in the highly developed areas when it's all concrete?
So that's a great question, right? Because let me go back to this. So if we're on that, there is some infiltration there, right? You can see some of the infiltration going into there. Because not every single inch is 100% paved over, but I mean, even if it is asphalt and concrete, it still will allow some moisture to soak in a little bit over time. I mean, there's little cracks here and there and things like that. So I think that's one of the reasons that they're trying to show it like that. But it's much more impervious or much less likely to allow infiltration to happen than, say, barren land or something like that, right? So, all right, awesome. Some other interesting tidbits here. I don't know, let's see. Group, did you hear from a group 2? Anybody from group 2? You had a lot of awesome, interesting things. Paste it on there.
Yeah, we also noticed the exclamation point and we were curious what that meant. And we also noticed that it wouldn't come up for, I believe it was the forest, the grassland, and the wetlands. Like it wouldn't come up at all, no matter how high we set the precipitation.
Ah, all right. So if we go like, oh, like, okay. So that's slow infiltration. So maybe if I do this or this or this, maybe if it's on high infiltration. So if I have something that a soil that really drains super fast, it doesn't matter how much it rains. It looks like it would just be able to be absorbed and go down without creating too much runoff. That's dangerous, right? But look at what happens if I change the soil there. So if I start changing the soil so that it changes how quickly the water can move through by changing like the porosity and the permeability of it, yeah, you can see that the runoff starts getting more and more and more. Because if water can only soak in at a certain rate, you keep adding more water faster than it can soak in, it's got to run off eventually. So those are good questions. All right. Let's see here. What was that, group 2? How about group 3? How about somebody from group 3? Did you want to share one of your ideas? If you could. 1, 2, 3, not it. Oh, all right. So we'll kind of look at it. So it says there's no runoff on the wetlands. And let's see here. So if we go to the wetlands like that, yeah, it took a lot of rain, right, in order for those wetlands to really produce runoff. And so runoff, remember, is water moving at the surface, not water that soaks in and moves down and around, but it's runoff so things that go into creeks and rivers and stuff like that. So because wetlands are on such moist soil and it's constantly kind of sinking into those grounds there, it takes a lot in order to raise the levels to make it so that it has enough to run off and get out there. So, I mean, that's 21 centimeters would be about 10 inches of rain, almost, that's a lot of rain. That's almost as much as we get in Turlock in an entire year. So some interesting things to think about. And I do want to go back just really quickly to the evapotranspiration issue of things. So we'll kind of put it on like normal-ish rainfalls or a heavy rainfall, or maybe like Turlock rainfall. You'll notice here that most of it infiltrates and there's a lot of evapotranspiration compared to like if it was just, well, grasslands and crops are very similar here, right? But if I have like barren lands where there's not as much stuff growing on it, the evapotranspiration goes down. If you have soccer fields or things, you're going to have a decent amount of evapotranspiration. But the big thing to notice here is when you have crops and plants and other things living on the surface, it's going to draw more water and put more water into the atmosphere than just, having barren grounds and where it just evaporates on its own. All right. Or shrubs and scrubs. So
Question.
Oh yeah, go ahead.
So I noticed that the runoff, there's no runoff in certain areas. Is that because it's drier areas, so it keeps the water from
so
I don't know how to explain it.
Yeah, so like in this one, for example, like a forest or something. Yeah, this would be like on a small rain, basically most everything would just be soaked right into the ground in the forest. And let's see here. Yeah, it takes a lot more rain for it to finally get runoff in this kind of scenario. So there's a couple of things. It's the amount of rain, it's the type of cover that's on top of it, right? That can slow the water down and help it absorb and infiltrate. So if it was landing on just pure concrete or barren rock cliff or something, it's just going to run right off. But when you have stuff growing there, it's going to slow the water particles down and give it time to infiltrate a little bit more. And so like if you have a really sandy soil, it's going to go down. If you have like a kind of a moderately sandy soil, it's still going to go down pretty quickly. But then you notice if we go to slow or very slow infiltration, then you start seeing more runoff. So it really has a lot to do with what the soil is like underneath those forests and underneath those lands, how much water it can absorb and soak up, and how quickly it can do that. So these are really awesome observations and notices and wonders that y'all have had. And I hope playing around with this gets us a little bit interested in seeing some of the other ideas. So I guess let's see here. Boop. So just kind of going over this, what type of soil, so that we just played, what type of soil here produced that lowest amount of runoff? So where the water wasn't running off, most of it was soaking into the ground. Which type of soil produced the lowest amount of runoff? I'll go back to, and you guys can chat it. You can like say it. Let me see here. Sorry. So out of those 4 choices, the high infiltration, the moderate, the slow, or the very slow, which ones produced like the least amount of runoff? Oh, let's see here. We got, yeah, the high infiltration soil. And so where you have areas that can soak it up, it just goes in there. Yeah, you got it. Good job. Right. And so then what type of land cover produces the most amount of runoff and why? And if we go back here, if we want to try to make that arrow the biggest and reddest we could possibly do, I think if we put over that high developed area where there's not much area to soak in, and we also put it into slow infiltration, so like the worst of all the worlds, where water can't soak in even once it goes through the concrete and stuff, you're going to definitely get a lot more runoff. And look at this, this is still a fairly small storm, but the majority of the water just runs off. I mean, 19 centimeters of that 21 that falls goes to runoff. And this is something that a lot of cities have to deal with all the storm drains and things like that. And in Turlock, we actually have ways to manage that runoff. We have those big sunken parks that people play soccer in and stuff. But when we have big rains, that's where the water gets stored from time to time. So something to think about here, because this is where your sketch notes are going to kind of derive from. It says, if you're a regional planner, like planning a city or a county or something like that, what kind of land cover would you recommend to increase the amount of water infiltration from a storm event? So if you had to think about it, like how could you change the land uses? You might not be able to change the soil types, but you might be able to change some of the land cover types to increase some of that infiltration. So that's something to think about as you move forward this evening. All right. So let me put some actual numbers on this really fast here. Let me shrink some things so I can see what I'm doing. Sorry. So here's, we kind of gave you generic ideas of high permeability, low permeability type of rocks and stuff. But over here is an actual chart. This is from the open textbook from British Columbia, but it kind of shows you of all the different types of rocks and soils and things that we've talked about, which ones have the greatest porosity, which means they have lots of holes and stuff in it. So some of those volcanic rocks that are fractured and have gas bubbles and stuff like that, some of those can be 50% cracks and stuff, and water filters through it very, very well. Like the background that you see of me there, that's a spring coming out of volcanic rock and a waterfall as well, which is pretty cool. All right. So these are the things that have those lots of spaces. Silt and clay. Look at that. Clay is like 70% empty space, or voids are filled with water or air or whatever else that's in there. All right. So there's a ton of empty space in silt and clay. And sand and gravel actually have like 40 to 50% porosity as well, which means if you had a jar full of gravel, you could pour a bunch of water into that and it would fill in the spaces in between those rocks. About 40% of that would be space to keep your water. So now that's the porosity. That's how much empty space there is between the grains. The permeability then is, or the hydraulic conductivity is another name for it, is how fast does that water move through? Well, look at this. Gravel, the water in the gravel moves through the gravel very much the fastest. All right. It's super quick. It's super quick. very, very fast. So this is in meters per second. So this would be like almost 1 meter per second, which is pretty quick. But if you take a look at some of the other things, these what we call unconsolidated materials, these are like our sediments. Clay, even though clay has the most porosity, it has the lowest permeability, or what we call the hydraulic conductivity. And so I'm going to show you why that is. There's a problem with the clay minerals as to why it doesn't allow for good connections to let the water flow between it. All right. So that's what we're going to take a look at in just a second here. So remember last week, we talked about the rivers, the watersheds that we had, the different drainage basins. The one right here is the Tuolumne River Basin. Then we have this Merced River and the Stanislaus River Basin right here. Well, when that water gets off of the granite and starts getting into areas that are more permeable, guess what happens? The water starts sinking down and permeating into the ground and starts filling up those voids with water until it gets to a point where it hits a layer on the bottom where it can't sink down anymore, an impermeable layer, or the fancy word for it is called a confining layer. I won't hold you to that, but it's basically a layer that water can't get through anymore, and it starts stacking up and filling up, right? And that's the beginning of what we call some aquifers. So I showed you last week, that's the headwaters of the Tuolumne, and that's where it comes from. But as those rivers start flowing downstream, a couple of things can happen. So up high in the mountains, usually what happens, we have what we call the rivers are a gaining stream, which means there's groundwater in the mountains as well that are kind of moving through some of the cracks of the rocks and things like that. But that groundwater flows into the rivers. And so the rivers actually gain a little bit of that groundwater as time goes on, as it flows across the surface until it gets to areas that have low or very high permeability areas. And what's kind of cool is that as those rivers go across like our valley sands and gravels and things like that, if the water table is low enough, which means the top of the groundwater underneath us, if that's low enough, and if the river, the bottom of the river or the sides of the river are higher than the water table, the river is essentially going to leak into the ground, and it's going to lose water into the ground and start filling up the groundwater table. So it's kind of interesting in California. If you're a farmer, you can live next to a river and a few hundred feet away, plop a well right here and suck water out of the ground and say it's groundwater, but really it's super connected to this river right here. So when you're pumping water right here, you're essentially pumping water right from the river, which is kind of funny. And you'll see that it's maybe not that funny, but it causes a lot of headaches in terms of water rights and things like that. So that's a gaining stream. A gaining stream means water flows into the river and the river gets bigger. Losing stream means as the river goes through, it loses and is leaking water into other areas. Okay, so oops, like I was saying, these areas in the Sierras, this is where you're going to have gaining streams because the rocks underneath are not super permeable, and it forces the water to stay in those river channels. But by the time it gets down into the valley, it starts infiltrating in and starts making some good groundwater areas. And that's our soils that we looked at from like 2 or 3 weeks ago. If you remember, you guys were playing around looking at the different soil types, and it's mostly sand. And we did those texture triangles talking about the different types of textures, the sandy loam, loamy sand, stuff like that. It's super good at draining. And if you know any farmers that live, near Hillmar or any of these sandy areas, they have to give their orchards a lot more water than an orchard that has maybe a little bit more clay in it or is more loamy, because their orchards drain so much quicker than some of these other places. So it's just something to think about. All right. Now, the big name, and I forgot to put on here, but we'll talk about it later on. This whole interconnected area of all the water that's under the ground, that's what we call an aquifer. And I don't know why I never put one on. So this whole area right here is an aquifer. All right. and that's blue, so it's hard to see, but you get the idea. So the aquifer is where you can actually pump water out, use it for a well. It's a usable place where you can pull water out from in between those cracks of the rocks and things like that. And that's what we're going to be playing with in our next model here in just a minute. A couple other things I also want to mention, and I'll get to you, Danielle, just really quickly here, is that the top of this aquifer right here, that's what we call the water table. So that water table can actually go up and down during the year. So after the wet season, when we've had a lot of rain and infiltration, you're adding to the water table. The water will soak down in and then start filling up, kind of just exactly like if you were to pour water into a glass, the level in the water in the glass rises over time. All right. And then this is what we call the unsaturated zone, or the zone of aeration, which means the spaces in between those grains are mostly air. And when it rains, the water just kind of goes through there like plinko, plink, 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 until it gets down to the bottom and starts filling up with the rest of that aquifer. So Danielle, go ahead.
So if all of these are connected, is it like a layer of the Earth's crust, like how there's different layers? Is there like a layer of water that we're just all floating on, or that's in between the layers?
That's a great question. Yes. So we're not floating on water, but in the Central Valley, a lot of the sediments and the sand grains that we have are filled with water underneath it. So underneath us, yeah, in Turlock, this is where we drink, is mostly groundwater. It's, a good chunk of that is the soil. It's the solid mineral material, but it's the stuff in between the pores that's water filled that we are sucking out. And in some places, we're going to see, we're going to investigate what happens if we suck more out than goes in on a yearly basis. It used to be balanced. And when Turlock was founded in the early 1900s, the Stanislaus County Fair started as the Melon Fair. People could literally just poke holes in the ground with the sticks, and melons could grow because the water table was only a few feet from the surface of the farms. But in the last 100 years, we've used so much well water and groundwater and not put enough back in that the water table is dropping. So yeah, we're not floating. We're not like sitting on top of it. It's solid. It's solid rock with, pore spaces and stuff in between it. But there is lots of water filling those pore spaces because we have there's layers of clay every once in a while that keep the water from going down. And so this is what your modeling is going to look at here in just a minute. So instead of me telling you, you'll get to play with it. So this is some wells in Turlock. These are the city wells in Turlock. You can see one of the fields where also they have like storm drainage runoff and stuff right over there. Some of it sinks back into the ground, but for the most part, the water that goes in after a storm gets treated by the wastewater treatment plant at a later date. And then these pull up water from hundreds of feet. And so just to give you an idea here of all the wells that Turlock uses, these are the ones that were active back in 2014. This is the latest data I could find. But look at all the gallons pumped in millions of gallons of all these different, oops, doggone it, aquifer is on there and I don't want it on there. Sorry, let me kill that thing. There we go. All right. So I just want to give you an idea of just how important groundwater is to a lot of our communities in the Central Valley. It's life. This is what we depend on. I mean, some of these wells produce over 600 million gallons of water on an annual basis. And that's just one well. Another well, 650 million gallons or so. And if you get contaminants in there, contamination, that can make it so you can't use those wells until they're cleaned up, or the soils are cleaned up, or pesticides are removed, or nitrates are removed. But those are all some different things that if you take an environmental geology or take Dr. Fariza's classes on hydrology at Stan State, he's the county hydrologist. So he is one of the world experts on groundwater and things like that. And he can tell you a lot of good things. I can give you a few more of the environmental aspects of it. So here's our second breakout that we're going to do. All right. You guys have been asking great questions. The second breakout here is going to go around these exploring groundwater movements. And so for this one, instead, oops, doggone it, you're not supposed to see that yet. on this one, let me find it here. There we go. Breakout groundwater simulator slides. Let me copy this link address and get it in there. All right, so breakout 2 slides. These are not a Jamboard. This is going to be slides. And oh no, did I not? Okay, give me one quick second because I forgot to duplicate this to make it group 2 and group 3 and all that kind of stuff. So I'm just going to copy that. I'm going to paste that down there, and I'm going to make these slides a different color maybe. If I can do that all at once. I don't know. Well, you guys can figure it out. All right, where each group, I'm just going to make a couple of copies here. Just start at slide 1, slide 2, slide 3, slide 4, slide 5, and rename yourself to the appropriate group, because I guess I made a mistake and I forgot to make the rest of it. But I think you'll be able to finish it, figure it out, no problem. All right, so there should be enough in there now. So you're going to go to this group 1 and slide 1. You're going to open what we call this exploring groundwater model. So you're going to click on this in just a minute, and it's going to open this cool little model. And you're going to just kind of ignore the little template thing that comes up right there. Just click close. If you're a full screen person like I am, you can click the full screen button down there at the bottom, and it makes it go bigger. Oh, need access. Okay. Oh, got it. Not on my A game, I guess here. Hold on. Let me shrink that. Let me give everybody access. All right. Should be good to go. Let me try that now. I misplaced my chat everywhere. Okay, try that and see if that works. Yeah, no, I see people. No, that's the wrong one. I see people popping on. Yes, people are popping on now. Okay, good. So you're going to open that groundwater model, and this is going to be, the slides here are going to represent kind of like your Jamboard where you record stuff. The idea here is in the yellow stuff, this is where you can jot down notices and wonders. You can make a bulleted list if you want. You can just add your own notices and wonders. However you guys want to format it, it's up to you, but this is kind of the recording space that I envisioned for you. All right. So the instructions are on each slide. So for the first one, it says select compare permeabilities from the template down drop down menu. So on our thing like this, if I make it big screen so everybody can see, here is your templates right down here. So the first thing we want to do and look at is the compare permeabilities. So you click that, and then it gives you this, oh my gosh, the cat. It gives you this cool little thing. You can click play, and you're going to get some raindrops, and it's numerically modeled. It's going to do a lot of cool little things, and you're going to be able to get to play and see what happens. All right. You can, if you want to play Rainmaker, you can add more water and things like that by clicking add more water. And in a few minutes, I'll show you how to add a well, or I'll do that in a minute. The rain probability down here, this is basically like we did on our last slider. You increase it, it makes it really rainy. If you decrease it, it makes it like more of a deserty environment where it doesn't rain very much at all. Okay. If you want to reset everything, you just click reset, and it does that, and it restarts everything. So for slide number 1, you're going to do that. You're going to press play, jot down your notices and wonders. All right. For slide 2, same thing or different thing, but now you're going to change the template to where it says confined versus unconfined. So you'll go to the template, go to confined versus unconfined right there. All right. And you'll have this. And it says press play and watch the natural flow of water over a 5 to 10 year period. And it says feel free to change the precipitation rate. Talk about your notices and your wonders. All right, that's slide 2. And on slide 3, this is where it says now add 2 flowback wells to, or no, it says 2 no flowback wells to the simulator. So let me show you how this works, because it can be a little funky and a little tricky here. So you'll see there's this little thing where it says add well. What we want is the non-flowback well, which means once we pump the water out of the ground, it's going to a city or something. It's not going back to a crop where it soaks back into the ground. Okay. And so on the instructions for that one, it says, so it says add those wells to the simulator as shown. So you can see I have one kind of in the middle of that hill and one off to the side of that hill. So do this to start with. And the way you do it is you click on add that well, the no flowback one, and then you click. And when you click on it, the longer you hold down, the longer your well shaft goes down. All right, the well bore goes down. So you want to make this one go into like right about there. All right. And then the second one is on the side of the hill, but it's going to punch down into over here like this. So you just kind of click and hold on. And if you mess up with the well and you need to remove it, you just click the remove button and you click on, oh, I guess you got to do remove well, and then you click on it and then the well will disappear and it does it like that. All right. And then you click play and you see what happens. So remember, these layers, blacks are kind of the no flows, low permeability. The pinks are the easier flows. All right. So that's what we're doing. And then slide 4 here, you're going to follow what it says for slide 4 and then put in a couple of wells just like you see here in slide 5. And once you get all your notices and wonders done with that, then we will have some conversations about what you notice and what you wonder. All right, so I'm going to give you about 25 minutes or so to play with this and experiment. You might want to have somebody share a screen, or you guys can experiment on your own. It's up to you, but collaboratively is the way to do it, I think. And let's see what you notice and what you wonder in these general patterns here. And if you want, you can change on your slides, change your group to the group that you're actually in. And I'll fix that for next time. But all right, so breakout rooms, here we go. And I'll do 20 minutes for right now. We'll see if that's enough time. I think that might be enough time. Where do they go? There they are. Sorry, it's been a long week. Can't find anything. Okay, here we go. Welcome back, man. You guys were making some really great progress. I was trying to call up a few pictures that I was thinking about that might help us as we go forward. So before I say anything else, I mean, you guys are filling out all sorts of amazing things. Anybody can share. I'm not going to go back through groups or anything, but who wants to share like some big ahas or something you noticed or have a really big question about? Let's talk about those really quick.
I have a question.
Mm-hmm.
So when I was doing some of them, like green bubbles will like come up from the top. What are those?
That's a good question. And I think I know what it is. Actually, I do know what it is, but I double checked. I saw somebody had asked that question. So that is supposed to represent evapotranspiration. So the water that evaporates and goes back up into the atmosphere, kind of like we did in the other model. And I think the reason they colored it green, I'm not 100% sure, but I think the reason they colored it green is because water vapor, when it gets into the atmosphere, is a greenhouse gas, which means we'll see when we talk about climate in a couple of weeks here and weather. It basically traps infrared radiation from going out. And so clouds are actually like one of the insulating layers in our atmosphere. Water vapor is too. So I think they colored it green because it's a greenhouse gas, water vapor is. So we'll see, some greenhouse gases occur naturally, and that's a good thing, because if it didn't, the earth would just cool off every single night to, a couple hundred degrees below zero, and that would not be good. So I think that's what it was. And some folks I saw in the notices and wonders mentioned that I see the green stuff coming off of like the black rocks, or the things that are not very good infiltration, and there was not green bubbles coming up over here in the places that drained better. And I think that's because if you have low infiltration, you're going to have puddles, and the more puddles you have, the more chances you are going to have a lot more evaporation and evapotranspiration and stuff happening. And if it sinks into the ground pretty quickly, it's underground and it can evaporate, right? So I think that's where that's coming from. So good observation and question. What are some other things, like in terms of the wells or layers or the way the water moved? What was like some big ahas?
We wondered what happens when that lower layer of the well is like dried up, when you've taken all the water. What happens to that space? Like, how does that affect the rest of the land above it?
It's a great question, and we're gonna talk about it. And so two things can happen. I'll just give you a clue. Is it depends on the type of sediment that the water, or the rock that the water has been withdrawn from. So different things can happen if it's sandy and gravelly versus if it's coming out of things that are clay rich. All right. And so I'm going to play this one. This is kind of what you guys were doing here. What did you notice when the wells turn on? What do you notice about the water table, or like the surface of where the groundwater is, the water table, the top of the water there? When those wells are pumping, does the water go down evenly, like if you're just sucking a straw out of a glass, or does it make some funny shapes? What did you guys notice? So I kind of notice, since nobody's hopping to it here, I kind of notice you get these funny looking depressions that look like that kind of. It doesn't lower the whole entire thing in a flat layer. It makes it kind of go like that. And the physics of water and water cohesion are what's to blame. How about if you look at my friend here in well number 3, if this is a rural area out here, what's happened to our friend out in well number 3 over time? It's the black number on there. Is his well getting anything, or their well, are they getting anything out there?
I believe towards the end they were, I think. When I did it after some they start, I think this is the one. Was this the last slide? If it was the last, then they end up getting like Nothing, I don't think. I don't believe.
Okay, so it can do, I mean, and it also depends on the wells that you, how deep you put your wells in and things for sure. Yeah, and if you look at number 3, so some of them it could have, and for this one right here, you can see there's no blue going up because his straw or their straw is not long enough to get down into there. But maybe if you have a good rain year, oops, I'm trying to click the wrong thing here. If you have a good rain year where you have a lot of rain, oops, no, not, I don't want to add another well, but oh well. If I add some water here, extra water, and play that. Oh, now we're getting a little bit more production almost into number 3, but number 4 straw is so deep, it just keeps sucking everything out. And you notice number 1 over here in the city, that water, when it starts trying to infiltrate back into the aquifer over here, it's pretty much being sucked up and diverted by this right here. And it's not having a chance to get over to well number 2. So that was, I thought, pretty interesting. How about this one? So this was the confined versus unconfined. And basically what this black stuff represents is kind of like a layer of clay. And we have water that sits on top of that clay. And there's groundwater that, so clay is not 100% impermeable. It just takes lots and lots of time to get through it. So the water that's underneath here is probably going to be much older. And when you put the wells back here, what's wrong with the folks that have driven down their wells into layer number 2 over here? What was the problem after that? So like number 2 just went to that top aquifer. Number 1 here, let's see, after time.
I don't think it really gets much water down there.
You're right. And so you can see like the production of that one in the blue is just pretty much, it's it. I mean, there's lots of water coming in above it, but nothing is infiltrating fast enough to be sucked up. And in the valley, we have what we call lenses of clay that basically keep the water up high. And sometimes the clay layers are a little bit lower, and they're not all like a perfect layer of cake icing or something that would spread across. So they're kind of punctuated from here, different places. But what that does is it sets up situations just like this across the Central Valley, where sometimes you get lots of infiltration very quickly and shallow wells can pump up, but sometimes if you drill too deep, you're drilling out water that is really old. It took many years to get there, and it's not going to be replenished in your lifetime. So just something to think about, which is pretty awesome. And yeah, so I'm glad you got a chance to play around with those different things. And oh, I don't know if you guys saw it, but there were also, no, doggone it. If you didn't see it in the drop-down menu, if you want to play around with it later, you can follow the water droplets and see how they're going. But the big thing I want to show you, they have the gaining streams and the losing streams. So you notice the groundwater water table is higher than the river, so it flows in, and then the river will carry that water downstream. So this is what we call a gaining stream. And then they had the losing stream too, where the water table of the river is higher than the water table or the top of the groundwater, and starts losing into the groundwater or into the ground like that. So that's our losing stream that I was talking about earlier. I just wanted to show that. So in our valley, the thing that you guys were just witnessing with that funny shape when the wells were pumping it out is what we call a cone of depression. And because of the molecular structure of water, when you suck it down or draw down, that cohesion or the way the stickiness of the water kind of makes it go down in this cool cone shape here. And so, for example, in this depiction here, this is from a well like in the Midwest that use sprinklers where they pump water out of the ground and then they put it on sprinklers. But if you have a very, very, very deep well that's deeper than the other folks, you're going to draw down that water table, and it's going to do it in this way that looks like this, or it's going to create this cone of depression. And what this essentially does is it creates a water gradient where the water starts flowing down like this as it lowers the water table over time, where it's going to get lower and lower and lower and lower. And so this was something that we had a big issue with during our last drought here in Central California. And I'll show you that in just a second. What I'm showing you here, this is a cross section of Turlock. So if this is the, imagine I drew a building right here. So let's say here's a house. I don't know why my pen is in yellow, but that's a really bad house. Pretend that's a house, all right? Or here's a person standing on top of the ground. So if you're drilled down into the ground, this shows where the different aquifers are in Turlock. And each one of these areas are clay layers that are confining those different aquifers. So this water, it's hard for the water to infiltrate down past what we call the Cochrane clay. And the Cochrane clay, I should say, is the remnants of an old lake that used to exist in the whole entire Central Valley many hundreds of thousands of years ago. And so sometimes if you were to extend this out and go into the mountains and the foothills and stuff like that, sometimes the water infiltrates in from the mountains and gets into these layers like that, and a little bit of the water has infiltrated through the clay. But long story short here, these aquifers are separated from one another by that clay. They don't mix with one another. And so when you drill a well down into here, this funny little thing that you see is what we call a well screen. Those are basically holes that allow water to flow into the straw that then the well sucks up for the city to drink. So this one has a big old well screen. Oops, let me see if I can change my color. There we go. This one has a screen that goes from about 150 feet all the way down to, what is that, 480 feet. It's all screened. So any water that's in here will start flowing into there and then get sucked up, or flow into there and get sucked up. Kind of interesting thing. All right. So we have gone down deep in many places. And this is just what it happens to look like in Turlock. But check this out. During the last, oh, doggone it. Sorry, I'm trying to get an eraser here. During our last big drought back in 2014 and 15 and 16 and such, people's wells were going dry. Those Kona depressions were getting deeper and bigger, and there was no water coming in from the rivers to irrigate crops. And so farmers were getting permits freely to go and drill brand new wells. And once you drill a well on private property in California, you are the owner of that water. Even though that water is connected underground to other things, it doesn't really matter. If you have the biggest well and you can pump more than your neighbor, you get those water rights. And that's how the way it used to be, and how it's going to be almost until the year 2043, when the new Groundwater Management Act takes place, because, well, water should be a right that everybody has. But during that drought, they had at least 170 new wells drilled to get down into that deep water to get the aquifers that, so I can go back maybe. Hey, go back. There we go. To get the water down in these lower aquifers, because the shallower ones were basically starting to get pumped dry and not enough water was going in to fill them back up to pump water out anymore. And so they kept digging and digging, and some of these wells went down over 1,000 feet. And what that happened locally is folks in Denair and some other cities outside of, in the rural areas that didn't have city water supplies and stuff, they were going dry because larger wells, and for the most part, those wells were agriculturally based, were pumping water so fast and so hard that it was leaving these older folks high and dry. Maybe their wells only went 50 or 60 feet down, and some of the new wells for the ag folks nearby were going down several hundreds of feet. Just more straws in the ground sucking out that water. And these folks couldn't afford to drill deeper wells. And so they were left high and dry. And that's what spurred some of the new legislation known as the California State Groundwater Management Act. One other thing that I want to show you here, this is kind of a funny map. This is the San Joaquin River on the left, the Tuolumne River on the north, Merced River on the south. This whole area in between the black lines here represents the Turlock water basin, the Turlock groundwater basin. And so this is all the groundwater that's in our area. The stuff in purple, and basically Turlock is right around, this is Turlock, or no, this is Turlock, sorry. This would be like Delhi, things like that, Livingston, I think. No, Delhi, because we haven't crossed Livingston yet. So Turlock, and then this is the southern part of Modesto. So Turlock Irrigation District has a lot of rights in this area in terms of managing that. So they work with the city of Turlock and the city of Modesto to try to make sure that we don't draw too much water out. But check out what happened. These lines that you see in blue, these are like topographic lines, and it tells you the level of the water table. So how high above sea level is the top of the water table? So right here, back in 1960, the water table was 120 feet above sea level. The ground here is about 120 or 130 feet above sea level. So if your ground's 130 feet above sea level and the water table is 120 feet above sea level, that means you'd only have to drill down 10 feet to hit that water, right? That's what this means. And you notice it gets lower and lower as you get towards the river, because the river was near sea level, and that groundwater actually flows out to the San Joaquin River and then out into the Delta eventually, which is kind of cool. But I want to show you how this changes over the years. So starting in the 70s, there were starting to be some droughts, and you notice the groundwater levels went from 120 feet and in some cases down to 90 feet. So pumping started causing these cones of depression that made the water table like 30 feet lower than what it had been. Then by 1986, it went from 120 feet down to 70 feet above sea level. So the water table had dropped 50 feet. All right. By the mid 90s, late 90s, some places were so bad it was only 40 feet above sea level. I mean, just that huge cone of depression of so many straws sucking out so much water. In 2002, it looked like that. In 2005, it just got worse and worse and worse. Kind of stayed perpetual. I mean, now we know a little bit better about how aquifers function, and so we're trying to keep more water in there. And I'll show you how they do that in a minute. But in 2014, when the folks started drilling new wells, the wells that weren't private, the ones that were publicly based, we could actually take the water from there, and there's isotopes, radiometric isotopes that are in that water, just like we talked about in the first or second week of this class, where you could use radiometric dating to date the age of fossils or rocks or things like that. You can actually do that with water too. And so Dr. Scott Jaseko right here, he helped me out. He found some of the data because this is what he does. And he sampled 403 valley wells. But check out how old some of the groundwater age was, depending on how deep the well was. So basically, the deeper you go, for the most part, the older the water was. And so in some of these areas where you have deep water that's fairly young, when I say fairly young, here's 10,000 years old, here's 20,000, here's almost 30,000 years old. Some of this is only 5,000 or 6,000 years old. But regardless, the deeper down you go, you're pumping out water that is very, very old. This is water that got it in place during the ice ages, like when mastodons and saber-toothed tigers and stuff were walking around in Turlock in that area. That's how old some of this water was, and this is what they're pumping up. So another name for this is like fossil water, even that kind of a kitschy name for it. But we also notice at the very surface, the water is very old at the surface. And the reason for that is because when you pump out water that's really old and then you apply it to your crops and fields that are on the surface, that old water goes right back into the ground pretty quickly. And when you sample it, that's how you get these old age returns on that. So the thing I want you to think about is this sustainable? If we're drilling out water that's, 6,000 years old, is that a sustainable practice and a sustainable source of water to rely upon? And so now here's the big question. Somebody was asking earlier about, were we, I think it was Danielle, are we like floating on water or anything like that? Remember, we're not floating on water, but in between those pores, or the spaces between the minerals, are water. And what's really interesting is that clay, since clay comes from granite and it's kind of silica rich, right? It's derived from granites, it's silica rich. It has a property that is a little bit more electrically charged than just run-of-the-mill bigger pieces of gravel and things like that. And what that does is water likes sticking to those charged surfaces, because water is kind of what we call a polar molecule. And long story short is the water likes sticking and coating to those different clay particles, and it holds on tight. And because it holds on tight, it's hard for water to move. It just wants to keep it stuck there, and it doesn't flow like it flows through sand or gravel or things like that. So that's why we see, even though sand and silt and clay have way more porosity or way more spaces on the overall volume, it's hard for the water to move. But there is a lot of water there. And if you drill into it and you suck it out, well, here's the problem with clay. All right. So we talked about the aquifers and those confining layers of clay and things like that. And in our picture of the Central Valley, if you were to cut it off, this is the San Joaquin River. This could represent like the Tuolumne River or something like that. Each one of these little areas in black or gray could represent a layer of clay from the old like Corcoran clay or something like that. There's water in there. And if you notice on the west side over here in the Coast Range, there's more black clay layers than there are over here. This is more sand and gravel. This is more clay rich. So here's the problem. When you have all those granular clay and silt particles that are full of water, they're kind of all disorganized and they take up a lot of space. But when you start pumping water out of those spaces, even though it's hard for the water to flow out, you can still suck it out. Once you pump that water out, those clay particles that are kind of spiky, all of a sudden, there's no water in between them anymore. And you have hundreds or thousands of feet of sand and soil and dirt on top. It causes those clay particles to squish down and go flat. All right, it'd be like taking a sponge and squishing a sponge down so that there's no more holes in that sponge to soak up any water. And so not only is everything going flat, but it can't hold water anymore. And this is the result. So in the Central Valley, we have a big issue called subsidence. And I don't know why I didn't put that on there, but in the west side of the valley that is built primarily on clays, over the last 100 years or so, since we've been pumping groundwater out, some places have dropped. And like you see this person, from 1925 to 1977, the land has literally dropped and collapsed in now about 45 or 50 feet in the last 100 years. So seriously, all this stuff, all the water that was underneath there was sucked out. And because they were on clay, those clay particles squished together. It doesn't happen on sand and gravel. Sand and gravel are more sturdy. They don't compress and compact like clays do. So that's an issue. When you suck the water out of clay, it can never get back in and you get subsidence, which sucks for our canals, because the canals that take water from Northern California to Southern California, if they are going like this and all of a sudden the land sinks, it makes a downhill and you can't deliver water as efficiently to Southern California anymore. And then even from 1965 to 2013, that's how much the land dropped. And then during our last drought in 2014, what's really amazing, I'll show you in just a second here, is that we had NASA using satellite data to track how much the land was sinking. And so over on the left-hand side, what you see here is kind of a fakey version of what a satellite view would have looked like in the 1800s of California. If we had satellites in the 1800s, this is a good idea of what it would have looked like. We had that Tulare Lake out there. Tulare Lake, a lot of people don't know existed, but it was drained to farm. But because it was a lake bed, it used to have lots of clays in that area. So this whole area is clay rich, clay sediments and things like that. Fairly productive to farm, but when you don't have water and they start pumping it out, this is the result. So these colors that you see overlaid on the map here, this is the valley subsidence, or how much the ground sank from between May 2015 to September 2016. And in some areas, it sank 2 feet. So in order for the ground to sink like that, that means they had to pump out so much groundwater that it allowed that to compress and to sink. And you notice up here in Turlock, we have no subsidence because we have that sand and gravel, and we're not built on those clays. And so we don't sink when we withdraw the water, which is kind of good because it also allows, this is the same thing, but it allows us to put water back in. So I gotta get going here so we can finish. But so how does this lost groundwater storage compare to everything else? Well, if you put it into context here, all right, oops, doggone it. If you put it into context, in the Central Valley, groundwater storage, there's about 5 times more groundwater storage in the Central Valley than there are in all of the reservoirs that we built dams for, okay? So we've lost since 1962, we've basically lost almost 60 million acre feet of groundwater storage in the Central Valley. That'll never be able to come back because the clay particles have been squished and we can't fill it up. And there's a map, if you guys want to check this out, this shows you all the different areas in California that are overdrafted, which means we've taken more water out than has gone in over the years. And so we need to fix that so we can put more and more water in so that we don't have these problems during drought. But to put it in context and perspective here, all of the dams in California hold about 21 million acre feet. And this is what the dams look like back in February 2015. And then we got some rain in 2017, which got them up to almost above average. But to put that in perspective, we've already lost 60 million acre feet. We've lost 3 times more storage in the valley down here than all the dams combined. So the groundwater is a really big way to sustain us for the future. It's a good way to put water. It's a good place to put water. So how can we get it back into the ground? Well, let me show you.
Roughly 100 million acre feet out of the groundwater aquifers in the Central Valley. So that is, a void that can be filled again. We have very well-known groundwater depressions in Sacramento County, more or less under every major city around Fresno, for example. Tulare Basin is known for having really, really depleted groundwater aquifers. So those all have room to take water again.
The idea here is that we want to apply
some of them. If you have the gravelly and sandy area, you can put it back in. But if it's clay, it makes it really hard.
Water to an almond orchard during the winter time when the crop is not using much water, so that the water goes through the soil and gets down and recharges the groundwater.
We want to apply 2 feet of water in December and January. In addition to the natural occurring rainfall, and then we will monitor the tree response to that additional water to see if there is any root diseases that are developing, or is it impacting the yield in the following summer.
This water right here is coming directly from the rainfall. City of Modesto collects it and dumps it into the irrigation district's canal system, and the water that's in the canals is being directed so that we can use it here. The ideal situation would be that it's a benefit not only to the groundwater, but it actually is a benefit to the orchard itself. It may be a good thing, you're running that risk, but I look at it as it's a risk worth taking if it becomes a benefit and can help a lot of people with the groundwater.
And so they recruited farmers to work together to they basically paid them to do the experiment to put it in there. And the last I saw with the study, it was pretty successful. It helped recharge parts of the groundwater in that area. It wasn't a whole bunch of water, but it did. And the trees didn't suffer any bad damage. It actually, the ground stayed a little bit moister, so they didn't need to water as much that following summer either, which was kind of a cool thing. So this is what we call groundwater banking, is when you have runoff or quote unquote excess water, you can put that into big areas where it can infiltrate in, and then you store it to pump out a little bit later on.
We've pumped.
Yes, we know that. The city of Roseville up by, let's see, somebody said something. Oh, it says, but if we are in a drought, will there be water to be put back into the ground? That is a great question. And so that's an issue. And no, So when we're in the drought, there's not much to put in there at all. I mean, there's barely enough water for farmers to get their allocated bits right now. The folks that are on the federal canals and things, they're not going to get any water this year at all. And they're looking for ways to buy it. So the way to do it is they have to plan ahead when we have these really wet years with above average rainfall and above average runoff, to take some of that extra runoff and find a way to put it in the ground. And in Roseville, they don't have really good infiltration areas on the surface. So they find ways to gather all that extra water from some of the lakes and stuff nearby, and they actually inject it or pump it directly into the ground. So instead of sucking water out of the well, they basically blow water back into the well and push the water in. And then in times of drought, then they can suck the water back out and use it again. So that's another way of storing it in this groundwater banking. And one thing I just want to call your attention to, if you check out their website, it says, oh, you know, excess surface water, such as flood flows that would have otherwise gone to waste. That going to waste, quote unquote, it's not going to waste. It's going through different environmental factors, and there's other benefits to it going through. So it's not a wasteful just going to the ocean. And I just want you to recognize and know that. However, you can still take some of that excess water and store it and apply it down here without harming too much some of those flood flows. But there is a lot of the environment and ecosystem that is dependent on flood flows to regenerate and rejuvenate. So think about pumping into the ground, how kind of cheap that kind of is to just put a little building in to pump water in versus building multi-billion-dollar dams that are around California that we have that have multiple different environmental challenges, right? So not only environmental challenges, but they have to make sure that they're seismically good. And a couple of years ago, we had those floods that almost washed out the Oroville spillway and almost took out the dam, which would have been a huge disaster. So if we can find ways to get it back in the ground, that seems like a more cost-effective thing. But dams you can build pretty quickly, and you can see the water there, and it's a tangible thing that people like to see. And then in Turlock, so these are some of the choices we have to make, right? In Turlock, our city water is going to double because we're going to start pumping out of the Tuolumne River instead of just the groundwater. So when we have droughts, we can use, or when we don't have droughts, we can use some of the river water coming out and allow more water to soak into the ground to recharge our aquifers. So I just want to show you this graphic really fast too. Some historical context in terms of droughts in California. Holy moly, right? We've had 30-year droughts, 40-year droughts, 25-year droughts, 22-year droughts, and 2012, and we probably never really exited the 2012 drought till present. One of the driest bits in the last last multiple thousand years in California is the drought that we've been going through. And on the east side of the Sierra, what's kind of cool is in the Walker River, there are these tree stumps sticking out. But if you do the tree ring dating on them, they're over 2,000 years old, or right around 2,000 years old. And basically these show some of the old, or 1,000 years old, I should say. These were growing in where the river is now because there was no river, because there was a drought over 1,000 years ago. And so these trees grew big. And then when the rivers came back, it deposited soil and sediment around them very quickly and kind of buried them and preserved them. And they're like fossils that haven't rotted away right there, which is pretty crazy and pretty cool. And so the ironic thing in California here is we built all this infrastructure in California along the San Joaquin River and all of our rivers in a time of relatively abundant waterfall. And even though this doesn't have to do a whole super bunch with groundwater, I just want to give you some geographic context here, right? 2/3 of California, 2/3 of California's rain is above this black dotted line, but 2/3 of California's population lives down here where there's only 1/3 of the rain. So most of the people live here, most of the rain is up there. How do we rectify that? So you're right, you have Northern California with versus Southern California in those pictures there. And so the way we deal with it is, right, we have dams and we try to modify different streams and things like that and get the water to where it's needed. And
Your picture is still on the lake with the tree.
right here, this one?
Oh, no, it was on the other one. Now it's there.
Oh, okay, sorry. Yeah, it's a little laggy tonight. I apologize. So I just want to kind of put this to you in another context here, which is pretty crazy. But in California, 19% of all the electricity we use in California goes to pumping water or moving water around in California, which is pretty intense, right? So almost 1/5 of every bit of electricity we use is water related. Kind of cool, kind of scary. But when we talk about climate change and shifting economies and things like that, this is one of the things we need to think about, is how that water moves. And so for us, Turlock Irrigation District was the first irrigation district in the entire or in California, not in the United States, but in California. They formed in 1887 to divert that Tuolumne River at the LaGrange Dam into the canals that you see in Modesto and Turlock today. We have the Hetchy project, which diverts water from the Tuolumne down to San Francisco. And then we also have some federal water projects that take east side water of the Eastern Sierras down to Los Angeles. So folks in San Francisco drink water from Yosemite. Folks in LA drink water from over by Mono Lake. It's kind of an intense thing. And since that time, that's my son when he was really little, but salmon runs have plummeted on rivers. And so we're trying to figure out ways, how can we boost the environment to make sure that salmon can thrive? Still kind of ongoing debate. LA took so much water and diverted it so much water that Owens Lake used to exist over on the Eastern Sierras, and now it's just a dry dust bowl. And so they were sued, and since 1998, they were basically sued by the folks that lived there because the air quality was so bad and causing so much asthma and lung damage. They've spent over $2 billion to try to keep the dust down. And instead of just keeping a little bit of water in the lake, they instead invested $2 billion to put sprinklers on it and try to and sprinkle the lake to prevent the dust and things like that. And that's kind of what the sprinklers look like. Until it was just a few years ago that they figured out, oh, if we plow really big troughs into the ground, the plowed up dirt actually knocks the air. It's like a snow drift where it disrupts the air and it allows the sand and sediment to go up and over and then settle in these berms. And then they replow again the next year. So they've kept the dust much better control in the last few years. And it also creates fewer ponds of water that turn toxic for these birds. But back in the day, that's what Owens Lake used to look like. And now this is kind of what it looks like as they plow the lake to make sure the dust doesn't get everywhere. But yeah, I used to have steamships and everything. So California water has been a really interesting legacy that you can do a whole class on. We have the State Water Project that has 34 reservoirs, 700 miles of canal, 25 million people rely on their drinking water for that. We have the federal water projects, which are like the Delta Mendota Canal you may be familiar with, which literally pumps water from the Delta back into the San Joaquin River. Salmon River runs were extirpated. It was pretty crazy. So that's basically the gist, the basics of where your water is and the groundwater, and just kind of an overview of all the different water projects here. Used to be able to take a steamship from San Francisco down the San Joaquin River to Fresno, believe it or not. And diversions have happened, so that doesn't happen anymore. But we're working to restore some of those rivers because it's not just good for the environment, it's good for our own sustainability. If the environment can't be sustained, we won't be able to be sustained in terms of being able to pump water out and such. So I also put a link on here for this. It's My Journey Down the Apocalypse River. It's an amazing, interactive, long read. If you're interested in reading it, it's not an assignment. Everybody's got too much to do, but we'll go with that. All right. So for tonight, that's kind of it. Sorry, we've kind of gone a little long, but you guys were really awesome. I'll do an asynchronous introduction to kind of your final project here coming up. Now, I'll probably release it maybe tomorrow night or something like that. It'll only be 5 or 6 minutes long. Don't stress. Next week, we'll go over it in a little bit more detail. And it's supposed to be fun. It's a Google Earth thing for those that just got here. All right. So really good job. Thank you so much for being here tonight. Let me give you some sunshines and blues. And there's a lot to think about, right? A lot to think about. And you guys are part of this system. And now that you know a little bit more, you can hopefully make informed decisions when it comes to being and doing that kind of stuff. And this is really the generic overview. Oh, I know. One of your questions too, and your sketch notes are like, how are some of the ways that you can increase infiltration and things like that? In Seattle, they use really cool little called bioretention ponds, where they rip out gutters and they dig little holes, and that's where the water sits. And if you look at any new gas station in Turlock, ones that have been built in the last couple of years, you'll notice on the edges of the parking lots, or even on Costco and stuff like that, there are these big ditches with plants growing in them on the side of the parking lots. That is what catches all the storm runoff. And the plants kind of filter out some of the toxins, and then the rest of it filters into the ground and starts recharging the groundwater. So they're starting to build that in to planning in the future. Right, so that's something to think about. And I'm looking for my, what do you call it, chat. There we go. All right, sunshines and blues. Thank you very much, everybody, for sticking with it. And you did great tonight, and good job. And with that, I'll see you soon, I guess. I'll post another quick little video tomorrow night as well. And then look at those volcano links that I sent in. If you download the slides too, there's links to all the volcanoes. It's pretty amazing to watch. So good night, everybody. Thank you.